2015 Cassandra Summit here. Raise of hands, first summit this year? Wow, there you go. Raise of hands, first time introduction to NoSQL. All right, we've got a great talk over today with my colleague here, Sean Rawl. I'll let you go and take the stage here.
Thanks, Ed. So, thank you. First of all, welcome everyone. It's great to see lots of folks joining us this year. Starting someone yesterday, there were 145 people in the first summit in 2015, and we were just hanging around and having some talks about the basics of Cassandra. This is the early days. And if you know how long it has come, you sincerely appreciate what we have achieved this year. So without further ado, let me kind of deep dive. I'm Darshan. I run the product management group of DataStax. I've been here for about 2 years. Have been a customer of DataStax for 3 years before this. Deployed Cassandra for hundreds of millions of consumers across the globe for telcos and stuff. So, and I'm an engineer by heart, so please feel free to ask me any questions. So one of the problems that I see in the industry and such is that we talk about how great Cassandra is, and you saw what Patrick did and demolished the 2 data center cluster. But we do not talk enough of the whys. We do spend a lot of time on the whats, but we don't focus on why is this technology gaining traction, and why are the designs the way they are. And there are some contextual realities around it. So this kind of a part history talk of what's coming, why was SQL, and why is NoSQL, or NewSQL, or Not-Only SQL, or whatever the latest jargon is. So this is what I plan to cover, and really it's about, I picked 3 key things. One is the changing nature of how you do schema management, the changing nature of how you do modeling, and why the internals of Cassandra are the way they are. And the third thing is finally deployment characteristics, because at the end of the day, you have to manage and operate the systems at scale. So, you know, we folks in Silicon Valley are good at jargons, right? We like to create abbreviations, and then we create abbreviations for abbreviations, because, well, that's cool. So look at what the SQL industry gave us, right? I mean, there was SQL, there was relational database management systems, which were founded on set theory in the 1970s. You should normalize, that there's a third normalized form, there are joins. These are the principles on which lots of SQL systems were built, right? And so it behooves us to ask the question, why were those principles in place to start with? And many of these principles were created before I was born, so it's kind of a history lesson in that sense. But this is more of an empirical exercise that I spend a lot of time on trying to figure out, why is it that RDBMS folks tell you to do third normalized form? Why do they tell you to do joins? What is the context behind those decisions? So there's a lot of jargon, and you might argue that in the NoSQL space we have an equally strong jargon, right? Eventual consistency, NoSQL, denormalize your data, avoid the joins. Almost feels like we came 180 degrees apart from the previous world. And it's natural as customers to be confused. And I thought it's very relevant for folks who, like us, who are providing the solutions to kind of lay the ground straight. So let's start first with schema. You know, this was like the abbreviation SQL stands for structured query language. It stands for structure. Structure was the foundational building block for SQL. So you started with, you know, I picked Oracle, but really it's about RDBMSs. Most systems were designed so that structure was front and center. It was a rigid schema and it was inflexible. And you know, this is not a dig against RDBMS. This is just to say that having an inflexible outcome was expected and it was okay. You know, changing a database schema was considered a pretty big activity. It wasn't that you change your database schema every so often. So that's where we were. Then we went to the land of utopia and said, well, we want schema-free. Schema is stupid, changing it takes so long, we need to be agile, we need to be, you know, changing the schema all the time. And we said, let's go schema-free. The reality is, if you are even a little bit technical, you realize that not having a schema is actually expensive for both from a storage systems perspective and from an application perspective. Because either your application has to manage it or the storage system has to manage it, and you can't get efficiencies of scale when you don't have schema. So then came along, oh, so let's not apply schema on writing, but let's just apply it on reading. Awesome. That's basically saying you're going to make writes are schema free, but reads are freaking slow. And so you just took from one place and you give it to the other guy. We do this often. And in many use cases, this is okay, by the way, just to be absolutely clear. In cases like you are ingesting billions and billions of events and you really don't want to pay the penalty when you're ingesting events, but you're okay to pay the penalty when you're doing a MapReduce job or analytics or stuff, or a warehouse processing, it's okay to do that, but not for a transactional system. So finally, what it really boils down to, when you talk to enterprises, when you talk to people who are running operational systems, they do agree that agility is needed in terms of how you manage the schema. But what they really want is that schema should be easy to change. It's not so much about that read and writes should not pay the price of knowing the schema, but what I call is schema changes are O1 operations. In the RDBMS world, you went and added a column and you could actually have to, if you had a billion rows, if you ever had a table which had a billion rows, then it would take that long time. It was ON operation. Versus in today's world, we're talking about O1 operations. And this is true. I mean, you can try doing this on Cassandra and some other NoSQL databases. You change the schema, and it's literally returns in constant time, no matter how much data you have got in your table. We have some customers who are on record with a single table having 40 terabytes of data when they change the schema on that table, and that's possible. So that's kind of where the world is right now. We want to get the best ROI of managing the schema, which is easy to change. It doesn't change often, but when it changes, it shouldn't essentially say, I need a downtime, or I need some maintenance activity to do on it. It should be easy to change, easy to manage, and easy to roll out into production. So that's really what has changed in terms of the new world. So this is what I call, it's optimized for agility of change when needed, not for some theoretical optimum, which is what a lot of folks try to do. They try to optimize for a theoretical optimum, saying you will always have to change the schema. There is always only unstructured data in the world. The reality is somewhere in the middle. Yes, there is unstructured data, and that is growing pretty fast. But there is a semi-structured data set, which is not that trivial. Frankly, it's one of the highest growing in terms of volume of transactions, not in volume of data. And that has some sort of schema. And that schema needs to change, but it doesn't change every minute or every 2 minutes. It probably changes a few times a month, even if you're a startup. We're trying to do this. So really what you need is agility. So you need to remember that. So now let's look at 3 interesting things. And these are the bedrocks of RDBMSs and SQL systems, right? Normalization, joins, and referential integrity. So let's look at joins for a moment. What it basically means is that you have 2 tables, you're trying to combine them based on some common value, and you'll get some sort of result out. Right? Okay? So you're using values which are common to both, and you're trying to create a join and get that data out. Fair enough? Then referential integrity is such that you want to ensure there is some kind of consistency in the value of these data, because now, guess what? You're actually going to use these tables to create a join. So if you have messed up data sets and you don't have relations which are properly accurately enforced, then you won't be able to do an accurate join. Okay, so that's referential integrity. And the third, which I think is the most important, is database normalization. So without going into too many details, it's basically saying, try to minimize data redundancy. And I think of all these fundamental concepts, that one element is the key. It basically says you want to minimize data redundancy in a system. This is what it was designed for. Okay, so let's park this and try to figure out why would somebody design a system which minimizes data redundancy. It seems, as an engineer, I really like doing that, but why would you do that is the question. So this was, I think, a 2009, 2010 report, but it's still true. But let's look at data access, right? So you look at random access and sequential access. And what you see is that disks have pretty much 1:168,000 random versus sequential access cost. And this cost just keeps on getting worse and worse. What that really means is that you do one bad random access on a rotational disk, you pay a huge price. And it's, to understand this, it's really physics, right? You're moving a head of a rotational spindle and moving it to a place where you shouldn't be moving in the first place. And that actually causes wear and tear on the hard disk itself. But what's interesting to note is that while that pattern is common across SSDs, across memory, memory is actually 1:10, right? So it's nowhere in comparison in terms of where essentially the random access sequential patterns are for memory and SSD. You can do the ratio and it's ridiculously high. So, okay, so let's park this pattern. This is in the 2000s, late 2000s, and this pattern just keeps on getting more and more. This is essentially the amount of data that you store on a rotational media disk. And I'm focusing on rotational media. It might seem arcane to talk about rotational media in today's day and age, but stay with me. This is a logarithmic scale. The density per disk has actually gone through the roof. But again, remember that the cost of sequential access versus random access is ridiculously high on rotational media. So I'm going to tie those 2 points together. And the third point is the price. So the price per gigabyte over the last 25 years, when these principles were designed, has fallen to some ridiculous amount. And again, remember, it's a logarithmic scale. If I actually showed the actual scale, this would not make sense. So if you combine these three, and if you go back to the data redundancy principle of normalization, you start thinking, well, is this why they had suggested to minimize data redundancy? And again, I don't know. I mean, there are theoretical papers on why you should do normalization. But there is at least one empirical fact for us to follow, that the amount that you had to shell out to actually duplicate data or store duplicate data was pretty freaking expensive. And the density was high and all that bad stuff. So if you start combining these three things, how would you design a NoSQL system? And I took Cassandra specifically for its access tracking. And I took, let's just forget about distributed systems and all that stuff. Let's just look at one machine. How does one machine read and write data? If you took those three factors into mind. The first thing that you do is that when writes come, you write it to something called a commit log. And you essentially put a copy of it in memory. Okay? Remember again, memory is cheaper in random access and disk is cheaper in sequential access by a huge factor. Then what you do is that periodically you flush that in-memory structure to an on-disk image, which is immutable. Again, it's sequential access, not random access. It's immutable. Once you flush it, it's not changeable. You can't change that file on the disk. Yeah? And then your new write goes to the new mem table. And this happens under the hood with Cassandra. And this just process continues, and you finally get a bunch of SS tables that you get on disk, and you still have one mem table in memory, right? So there is a time period which controls this, how often you want to flush it, and control by time and size and all these other variables, which is interesting. But now let's look at reads. So what happens when you actually get a read? So if this was the pattern and you want to get a read, you would go and hit there's only one mem table to hit. It's an in-memory access. You'll go and read that from the memory, and if you don't find it in there, then it's not there because it's either there or it's not. The other option, and the next thing you need to do, is you need to merge across all these multiple SS tables, right? So you need to read one mem table and n SS tables, where n is greater than or equal to 1, at least 1. So you would ask, well, wait a minute, this doesn't make sense because now you're paying the read cost pretty high in terms of trying to access this disk system. Well, there are three things that help you here. One is the OS cache. What people don't realize is that a lot of OS is pretty good at caching stuff. And yeah, you can get around with it and you can shave off 5% or 10% after it, but OS basically does a pretty good job of it. The second thing that Cassandra does is it's kind of an umbrella term that I use called accounting. So one of the things it uses is something called bloom filters. And that essentially figures out that you should not be, which SS table do you want to access? So it reduces the number of SS tables that you want to touch. Because remember, it knows that if I have a key in one table, I can figure out which SS tables should I eliminate. It's not to say that I know exactly this SS table, but it is to say, these SS tables for sure don't have that record. I should only touch the few SS tables. So now again, you're not touching n SS tables, but you're probably touching n by some factor. SS tables were significantly small. But the third and probably the most important is that once that number of SS table reaches that certain point, you have to compact these SS tables into final SS table. And I've super simplified this because there are other compaction strategies and how do you manage this and such. But fundamentally, you come down to, okay, so I have one mem table and one SS table. This is utopia. This is the ideal state. This three combined actually give you a pretty good read performance. This is what Jonathan was talking in the keynote, where folks don't realize, they complain that your writes are fast, but your reads are slow. That's usually because you have not tuned the system correctly. Because you're not paying properly compacting stuff, you're not set the bloom filter properly, some of the other problems. But if you actually set all of these things properly, the read performance of Cassandra will beat the read performance of any other system by a significant amount. Not trivial amount, significant amount. But if there are two things to remember from this, from all the previous stuff that we learned, is that for disk, optimize for sequential access, and for memory, optimize for random access. Simple. It's as simple as that. That's the foundational principle that Cassandra got its birth in. And how do you do all of these things so that you don't have to incur the cost while keeping read and write latencies the same? And now if you just, what I just described here happens on every single Cassandra node in the system. Whether you're doing reads for whatever reason, this is basically the bubbles Cassandra. But really it's designed for that hardware characteristic, which is that random access, do in memory, and optimize sequential access on the disk. Actually, the shocking aspect is we had Intel here just before this, and if you look at a lot of hardware manufacturers, they are doing this in SSDs, right? And if you look at SSDs, this is what they call the log structure tree implementation. They under the hood, they actually do this. They have a small cache in memory and a big file system block because optimize this quite a bit. All right, the next one is the execution engine. So a lot of folks don't realize, but a lot of time spent on CPU is fundamentally what I call voluntary context switches. So think of it for a moment. Operating system is giving you 10 milliseconds of context for your program to run. And what do most programs do? They will process it for less than a few microseconds and then do I/O or block or content or whatever. Fundamentally, that's a context switch. And this was happening in 2000s on a 550 megahertz CPU. As the processors have sped up, the cost has actually increased dramatically. So there was this architecture created in the early 2000s called SEDA, Scalable Event-Driven Architecture, which basically says it's a foundational principle of breaking down a request into activities and aligning it with the amount of concurrency that you have on the system, and avoiding and minimizing context switches and having very good backstart event flow. So if you notice, the diagram actually represents a feedback loop where you have a batch of work that is actually going to happen. There are a bunch of workers, and there could be one, there could be two, there could be n. You choose based on the activity. You do the work, and then you push it out to the next stage. SEDA stands for Stage Event-Driven Architecture, and there are other models that are percolating now. But really, there was this piece, which is the holy grail of many of these systems, which actually provide you characteristics where if you try to hammer a lot at it, it will try to backtrottle. And frankly, I think there are very few distributed systems who do this last part very well because it's pretty expensive, and I think Cassandra is improving too. But that's the execution engine that was driven because you started having so many cores, the core speed started going up, and all you were left with was context switches on the system. And how do you optimize for context switches on a user level program? That's essentially what the execution architecture was optimized for. It just keeps on getting better. Again, I'm going to the really old history of Cassandra, but fundamentally this still stays the same. So the key takeaways are You want to optimize utilization of physical resources, right? Your rotation media, your memory, and CPU. And how you do that, how the software actually achieves it, can provide you dramatical improvements compared to what you can shave off by implementing a new algorithm. There is no read before write. If you notice, the reason why you don't do read before write is because read before write by definition requires random access. And so you don't do read before write, and I put well mostly because there is a caveat that I will come to in a moment. There are one or two areas where you have to do it for certain reasons. Plan for compaction. I like to call it like credit card debt or commercial paper. You're taking some hit in the short term because you have high load or you have peak capacity or whatnot, but you will need to pay it back. This is one of the most common problems that folks don't understand. And they argue that, oh, that's just stupid because I have to pay the price later on. What they don't understand is that if you, because of compaction and because you're not doing read before write, if you can perfectly tune and compacted system, it will actually deliver you better read latency over longer periods of time and a more deterministic read latency. And the last one, which was subtle but not so obvious, is this whole denormalization concept, right? So now that you have disks, which are cheaper, you have sequential IOPS, which is way out of line compared to random IOPS. And I'm just talking disks for a moment. And your primary variable to optimize is the application, because the response times to the end user is important. Because guess what? Nowadays applications can either serve global millions of users, or they may die in 6 months. So what you really need to optimize for is, it's okay to duplicate data if you want to give better response times. And that's kind of a fundamental shift that we have to do. And there are other things that we can talk about in depth, but really what this boils down to is that it's not a pattern that was not there. If you actually go and look at the literature of why second normalized form is used, this was a common pattern used in RDBMSs, for example, for telco stacks. In 2000 I was designing a voice messaging system, and you would never do joins. And the reason you would never do joins is because on a voice, the latency needs are microseconds, not even milliseconds. And you try to do a join, and you may have no guarantee how fast the query will return. We optimize for second normalized form and non-third normalized form, even in RDBMS. And you will get a factor of better performance just because of that. And yeah, there are trade-offs associated with it, because you need to manage atomicity and guarantee and all that stuff. But databases start to provide that, right? Cassandra gives you something called atomic batches. So when you write to one table, you can guarantee that it is written to both or none. We just talked about materialized views in the keynote, where we write to one table and then we create a view for it, because that view is optimized for a user query. And that's under the hood taken care for you. And yeah, it's not very, but it's still going to give you the most optimal TCO from a long-term perspective. Now let's look at deployment semantics. That's the third leg of the stool. And Jonathan covered this a little bit, but I think it's very important to hit this in front, because deployments is one of the key aspects for running an operational database management system. This is what, so let's start with a single box. Again, in the 1970s, you used to have a single database box, all happy and fine. It was a seasonal application. If you went down, you told the consumers, go back, I'm going to fix the database, come back after 3 days or a week or 2, and everything. That was the world that people lived in. Then somebody said, you need disaster recovery. If something goes down, you need a slave, things are not going to work fine, then you need at least somebody else where all the data is there. And yeah, sure, there is some kind of replication with all this lag and all that beautiful stuff. This is what used to happen in, for example, LDAP servers or DNS servers or whatnot. Actually, this happens even today in many mission-critical systems, shockingly. But then we said, well, but if there is one data center, the data center blows up, this is again starting to go into really mission-critical stuff. I need to actually position this for have another kind of slave. And if something happens, I'm going to do some manual process and bring that slave up to the master and all that funny stuff. Well, but if I really need geo-redundancy for a disaster recovery, I need yet another slave. This would actually give you a fully resilient system, right? A box going down, data center going down, and having a resiliency in the second data center where even the primary of the second data center going down. So really 3 years of resiliency is what this would give you. had all sorts of issues with regards to how you manage, how you upgrade, and the replication delays, the synchronization issues, all of that. But still, fundamentally, this will give you that 3 years of resiliency if you need it. But if you now came the scale issue, right? So you would do scale, and people would normally do, okay, let's just replicate this pattern as we go along, right? And just let's make more of these, and I just created 4 for the heck of it. And this also works till it doesn't, because essentially what ended up happening was that this is just 2 data centers, but if you start having 4, 5, 6, and not everybody has it, but there are demands for more and more data centers. What you end up happening, what you see here is that every data center seems to have 1/4 of capacity for writes and 75% of the capacity for reads across all the shards, right? So the deployment is fixed in terms of what write throughput you can give and what read throughput I can give. It's very interesting. Think about it for a moment. This was designed in a day when the world was in 70 to 75% read-only mode and 25% write-only mode. Guess what is happening in the IoT world? It's 90% writes and probably 10% reads in an analytical mode. The amount of writes, if you look at what some of our customers like Netflix and Apple do, is just mind-boggling in the system. So again, this was designed in a model that even if you ignore all the operational overhead which you had to do, which was not trivial by the way, and all the synchronization issues that you had to go through, it was pretty freaking big. And now, if you contrast that with Cassandra, and this is one of our salient points, but there are other people who try to do this, but no one is ever close at it. This is not just a architecture diagram. That orange box over there is a JVM. It's literally the JVM, meaning there are no moving pieces. It's exactly same as how it is across all the nodes on all the data centers, whether it's on cloud or it's on your own data center. And all the magic under the hood is taken care by Cassandra and its internals, which is pretty powerful if you think for a moment. And yes, under the hood it's doing and taking care of where the replica sets are and who's the hottest replica set and where should I route the query and all that stuff. But there is no concept of a master. There is no master. There is no maintenance when something goes down. Right? And most importantly, it is not tied to read or write throughput. So if you suddenly had 70% write in one data center and 30% read in another data center, you can scale up and scale down. There are customers who will deploy hundreds of nodes in one data center and only 5 in another and route all the read-write traffic that way, if that's what they wanted to do. Right? Some people will put rotational media on one of the clusters and they'll actually put hard disks or SSDs and in-memory storage on one of the data centers, and that's fine. Right? It's so powerful in terms of how this can work that there is no comparison. And I talked about this yesterday where people said, yeah, but I can do GR2, everybody nowadays, if you go around in the valley in this 50-mile radius, everybody will tell you that, oh yeah, you can do GR2. And when you start digging under the hood and try to find out, this elegance was built in Cassandra's architecture since 2008. This wasn't like a bolt-on thing that was added. So it's so freaking difficult to get georedundancy at this scale right. And what does that give you is essentially this linear scale. Right? So if you think for a moment, having no master allows you to fundamentally get this linear scale as you add more boxes. And most people forget, it's not just adding boxes, it's also removing boxes. Because if you have Black Friday, you're actually going to add 20 nodes. After Black Friday, you're going to take it down. So you can go up and go down the stack live in production, on cloud, on premise, because of that fundamental architecture that, guess what? You do not have different roles for your different processes. It's a very simple thing, but it's a pretty powerful architectural hedge. It's very hard to get right, by the way. If anybody has built a distributed system which is trying to do all of this in a single JVM process, it's very hard to make sure. So what's the catch? Well, in a distributed system, there is no lock manager. Right? There's no locking. Right? So it's hard to, people think, oh, how do you implement counting? How do you implement idempot encounters? RDBMS is very good for idempot encounters. Now we cannot do idempot encounters. Turns out that's actually not the